All right, so we're in section 13.3, and we're going to talk about permutations and combinations. And some of us, when we did the little vocabulary thing to see what ideas that some of us had heard of before, permutations and combinations were one that some of us maybe had heard of before. So hopefully that we'll talk about today. It's going to ring a little bit of a bell. The first thing I want to do is an example of how we count things in one kind of situation. So let's say we have 3 shirts and 2 pairs of pants. How many total outfits can we make? 6 outfits. And how did we get? How did you come up with 6? Multiply. Total outfits is 3 times 2 equals 6. Let me draw what's called a tree diagram to show why this works. So here's our tree diagram. I'm going to say shirt and pants. So here's shirt number 1, shirt number 2, and shirt number 3. For shirt number 1, I could wear either of these 2 pairs of pants. So I could wear pair number 1 or pair number 2. For shirt number 2, do the same thing, pair number 1, pair number 2, and we're saying that they all match. So we're not getting any that don't match really well. And same thing there. So I have 1, 2, 3, 4, 5, 6 possibilities for my outfits. So they call this little thing a tree diagram. That's how we come up with it. So 2 times 3, 6. What if we had 2 belts? How would that change our answer? Multiply by 2. So I'd have 3 times 2 times 2, and I would end up with 16, 12. And I'm going to put the belts over here in red, and I can do the same thing. For each pair of pants, for each outfit, I have belt number 1, belt number 2, same thing there, 1 and 2, same thing there, 1 and 2, same thing for this outfit, 1 and 2, same thing for this outfit, 1 and 2, same thing for that outfit, 1 and 2. And if I count all these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I end up with 12 possible things. And this is our tree diagram so that we have the tree and the branches. Well, in math, we like to give fancy names to things. So we have a name for counting things. This way when we multiply. So we call that, is everybody good with our example? We call this way of counting, where we have these different things that we're putting together, we call it the fundamental counting principle. So what the fundamental counting principle says is that one event occurs, and occurs just means happens. So event is something we're interested in. One event occurs in m ways, and that's just how many ways it can happen. So we have 3 shirts, so that event could occur 3 ways. Another occurs in n ways. So that's like our pants. Together, They occur m times n ways. So that's our fundamental counting principle. Something happens in so many ways, another thing happens in a different way. To figure out the total, when we combine them together, we multiply. That's what the fundamental counting principle says. Multiply. And if we have more events, we just keep multiplying by how many ways that event can happen. So we're good there. So that's one of the easier ways to count when we have a lot of things that we're putting together. So let's look at another example. Let's say we need a password. Made from 26 letters, or sorry, made of one letter. We gave away first part of the problem. And two numbers. Two one-digit numbers. How many passwords can we make? So we're just counting the ways that we can put all of these things together. And I'm going to say like M86. So that would be one password. So this is a counting principle problem. We're seeing how many ways we can put all these things together. How many letters do we have to choose from? 26. 26 letters in our alphabet. So this is letter. How many one-digit numbers do we have to choose from? 9. Let's say we can choose 0 also. 10. Okay. Times 10 number, and then for the second number, how many choices do we have? 10 again. Oops, and this is number. So we multiply these together, and we get 2,600 passwords. Yes. We want two one-digit numbers. So we pick our first digit out of 10, and we pick the second digit out of 10. Multiply those together, and we get 2,600 passwords that we can make from one letter and two one-digit numbers. You good with that? All right, what if the problem was a little bit different? What if we have no repeated numbers? Close. So let's break it apart again. Does it change how many letters we can pick? Now we can still pick 26. How many choices do we have for that first one-digit number? 10. All right, we can't repeat. So how many do we have left to pick from? 9. And when I multiply this out, I think this comes out to be 2360. Anybody have a calculator out? Check my arithmetic. 26 times 10 times 9, 260 times 9. What? Am I right? 2,340. So we have 260 less passwords if we can't repeat that second number. But still a fundamental counting principle. We're just seeing how many ways we can combine all of those together. All right, questions there? Everybody good with those examples? So this just gives us a way to count things a little more easily than putting them in a list and trying to count them. It gives us a bit of a shortcut. All right, let's look at another way. let's say we have 5 books to put on a shelf. How many ways can we arrange them? And I'm just going to say arrangements. Yes. Okay, very good. So let's talk about how we get that. So you picked it out already. The way I think about these is, let's say I have my 5 books sitting over here and my shelf is here on the table. How many choices, so I'm arranging all these things, I want to figure out how many ways they go together. So how many choices do I have for the first book to put on the shelf? If I have a stack over here. How many? I have 5 books stacked, so I can pick any of those 5 to put over on my shelf. So for the first book, I have 5 choices. Well, after I put one on the shelf, how many choices do I have left? 4. So I have 4 choices for the second. I put 2 on the shelf, how many do I have left? 3. So that's my third. And after I put 3 on the shelf, how many do I have to pick from? 2. And then finally on our last one, I only have the 1 book left there. So just like you said, I just wrote it in a different order, 1 times 2 times 3 times 4 times 5. And when I multiply this out, this comes out to be 120. So I can arrange these books, these 5 books on the shelf 120 different ways. I have 5 choices for the first book, 4 for the second, 3 for the third, 2 for the fourth, and then finally 1 for the last. This operation, taking a number and then multiplying it by every number smaller than it, 5 times 4 times 3 times 2 times 1, 6 times 5 times 4, etc., 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 comes up so often and in so many different ways that we give it a special name. So 5 times 4 times 3 times 2 times 1. And we also give it a special symbol. Does anybody remember what the symbol is? You might have seen it before. This is 5, and we put an exclamation point. And we pronounce this 5 factorial. So factorial just means take the number and multiply it by every number smaller than itself. So n factorial, if n is just a number, n factorial is the number times the next smaller number, n minus 1 times n minus 2, the next smaller, so we keep subtracting 1 from the number, times dot dot dot, and then we go all the way to 3 times 2 times 1. We start at the number and multiply by every smaller number than itself down to 1. And a special number is 0 factorial. In order for everything to work out right, 0 factorial has to be 1. So this is an important number. And we can't do factorials with negative numbers. They have to be positive numbers. Let me show you on your calculators where to find factorial. So let me get this calculator up here. If you have a Texas Instruments calculator, it's going to be more or less like this one. Some of the others are a little different. If you have questions, I can show you where to find these buttons on your calculator. So most of the Texas Instruments are going to be more or less like this. So I'm going to do 5 factorial. I'm going to go to this. Some will have a separate button. This one I go to the probability menu. This PRB means probability. I'm going to go to probability, and there number 3 is my factorial. So I'm going to go down to number 3, hit enter again, and it tells me that's 120. So if you have a Texas Instruments calculator, you're going to have a probability button, or somewhere you're going to have a probability menu, and that's where you get to it. Some of the older calculators are a little different. Some of the other calculators do it a little differently, but more or less the same. If you have a TI-84, so you go to the math menu first, and then you're going to arrow over to the probability menu, and it'll be in there. Find it? Okay. All right. Sometimes we want to count, and if you have trouble with your calculator, just let me know. I can help you out with a calculator. Sometimes we want to count not all of the arrangements of something, but only some of the things arranged. And that leads us to our permutations and combinations. So we want to talk next about permutations. And a permutation is just an arrangement. And we'll talk about what a permutation is. So the number of permutations of n things is just a number, arranged r at a time. So the one important thing about permutations is we're taking a smaller group out of a bigger group. So rather than talking about all the different combinations, we're taking something smaller, a smaller group out of a bigger group. Is, and we write NPR, is n factorial over n minus r factorial. And the arrangements with permutations is order matters. So your clue that you're talking about a permutation and not a counting principle problem is that we're making a smaller group out of a bigger group. And what I mean by order matters is you're going to have also something that says something about how you're arranging it. First, second, and third place. President, vice president, secretary. Something that tells you that a different arrangement makes it a different thing. So different arrangement makes it different. So a different arrangement is a different thing. So for example, if I talk about how someone can finish a race, first, second, and third. If I come in first, that's different than my coming in third. That makes it a different thing. It's different than if I come in second. So if I arrange those first, second, and third, that makes that arrangement a different thing. Even though the same three people could be finishing first, second, third, it's different depending on who finishes first, second, and third. So that would be our clue as to that would be our clue that we're using a permutation. When we do these permutations, we have to do the parentheses before we do the factorial. So we can't distribute this factorial. So let's look at a calculation. And our calculators, luckily our calculators do these things for us. So let's look at 7p4. On the quiz, I will give you this formula. So you don't have to memorize that. I will give you that formula. 7p4 is 7 factorial over 7 minus 4 factorial. I have to do these parentheses first. So this is 7 factorial over 3 factorial. So let me show you 2 ways to do it on your calculator. On the calculator, I'm going to do 7, and I'm going to go to the probability menu. And here we have this button that says NPR. So I'm going to hit the NPR button, and I said we're doing 7P4. I hit 4, 7P4, enter, and I get 840. I can also do it with the factorials. I said this was 7 factorial divided by, I'm just going to put it in exactly like we wrote it back here, 7 factorial divided by 3 factorial, 3 factorial, and I get 840. So I can do it either way. Questions there? All right, again, if you have questions with your calculator, how to do this with your calculator, I can help you out. This formula I would provide on a quiz or a test. So let's look at an example of a permutation. We have 10 people in a race. How many ways can we have a first, second, and third place finisher? All right, does the order matter here?
Yes.
Yes, that was the example I just gave, that order matters. How many things are we taking out of these 10 people? How many? 3. We're arranging 3 things out of the 10. So this is a permutation. Because order matters. Different people in first, second, or third place makes it a different way of finishing. So it's a permutation. So we have 10P3. And this is 10 factorial over 10 minus 3 factorial, or 10 factorial over 7 factorial. I do the parentheses first. Can't distribute this factorial. All right, let's calculate this. Go to our calculator, and I'll do it 2 different ways. So we're going to do 10. Go to the probability menu, NPR, 3 for our first, second, and third place finisher. Hit enter, and I get 720. I could also do 10 factorial divided by 10 minus 3 is 7, divided by 7, and I'll do the factorial there. 7 factorial, and I get 720. So either way works. And if I wanted to write this out the long way, this would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 7 times 6 times 5 times 4 times 3 times 2 times 1. So the factorial makes it a lot easier than writing out this thing. Anybody see a shortcut here for this last calculation?
You cross out 7, 6,
All the way down both sides. This is the same in the top and the bottom. So we can cross those out. And I just have 10 times 9 times 8. If I couldn't remember how to use this in my calculator, and 10 times 9 times 8, 720. Any of those three ways works. All right, questions there? All right, so we have a way of counting when we're just arranging things. We have something that can happen one way and some other thing that can happen another way. We multiply. We're taking a smaller group out of a bigger group, and order matters. We do a permutation. We have one other way of counting, a combination. We're taking a smaller group out of a bigger group with a combination. How are you going to guess this is going to be different than a permutation? It still has multiplication. For permutation, order matters.
Order doesn't matter.
Order doesn't matter. There you go. Combination. So the number of combinations of n things arranged r at a time. So we're taking a smaller group out of a bigger group is, and we write NCR. C for combination. You can also say N choose R. N factorial over R factorial times N minus R factorial. I would give you this equation on the quiz or test book. And this one is order doesn't matter. A different arrangement doesn't make it a different thing. So an example of a combination. Say we have 10 ice cream toppings and we can choose 4. Doesn't matter what order we put on the toppings on, it's the same ice cream sundae. If we have a sandwich and we can pick 2 toppings out of 7, switching the order of those 2 toppings doesn't make it a different sandwich. But I think it tastes better if the mustard is always on the bread. The mustard can't be closer than the mustard always has to be the last layer before the bread. That's just me. But it doesn't make it a different sandwich. A BLT is not different than an LBT. It's the same sandwich. All right, so let's look at an example here. Let's calculate 7C3. So that's going to be 7 factorial over 3 factorial times 7 minus 3 factorial. You can write that out, 7 factorial, 3 factorial times 4 factorial. One place to be careful here. I can't multiply the 3 and the 4 and then take the factorial. I have to keep all of these separate. I have to calculate the factorial separately. I'm going to plug this in my calculator. So we'll do a 7C3. 7, I'm going to go to the probability menu. And the second one, NCR. And I hit 3. Enter. And I get 35. And I can calculate it out just like this as well. So let's do that. 7, I'm going to do the factorial. Divided by, and I want to make sure I put some parentheses here because I want the 3 and the 4 together. divided by 3 factorial times 4 factorial, and I hit enter, and I get 35. So I can use the button here, or I can calculate it out just like I wrote it. Get the same answer either way. So remember, we can't distribute the factorial here, and we have to do the factorials before we do the multiplication. So a couple more examples of combinations. So we said toppings on a sandwich. Order of cards in a hand if you're playing cards. Doesn't matter how you arrange them. It doesn't make it a different hand of cards. You still have the same cards. If we make a committee, so let's say we're making a committee of 3 people. A committee, doesn't matter what order the people are on the committee, it's still the same committee. If we talk about a president, a vice president, and a treasurer, then that would change it. That would be a permutation because it's different depending on who the president is, who the vice president is, etc. All right, so let's do one calculation with a combination, and then we will be done for today. So let's say we can choose 3 of 10 toppings for a pizza. So we have a coupon that lets us pick 3 toppings out of 10. How many pizzas can we make? How many different pizzas? All right, so are pizzas different if we arrange the toppings differently? No, it's the same pizza, right? It's a pepperoni, mushroom, and sausage, whatever. Doesn't matter if we do sausage, mushroom, pepperoni, it's the same pizza. So this is going to be a combination. Doesn't matter what order they have the little toppings when they assemble your pizza, it's going to be the same thing. This is a combination. So we're doing 10C3. 10 factorial over 3 factorial times 10 minus 3 factorial. We write that again, 3 factorial times 7 factorial. Plug that in my calculator. So I'm going to do 10, go to probability, go to combination, picking 3, hit enter, and I get 120. So I have 120 different ways that I can make a pizza by picking 3 toppings out of 10. I was going to say, there's one other thing I was going to say. Oh, on a quiz or a test, I would ask you, so to show your work on a problem like this, I would want you to write out this formula, not just plug it straight into your calculator. Write this part out, so I know that you understand the formula, so you know what that formula is telling you. So this would be how you would show your work on a problem like this, on a quiz or a test. Questions there? All right, so we have 3 different ways of counting. Counting principle, when we're just arranging, figuring out how many ways we can put things together. Permutations, combinations are always going to be a smaller group picked out of a bigger group. The difference is with permutations, order matters. Change the order makes it a different thing. Combination, order does not matter. Change the order does not make it a different thing. Okay. Our homework is a worksheet.